Hello students, today we are going to discuss the new quantity angular momentum, which is analogous to linear momentum, as well as the torque or moment of force acting on the rotating body. So first quantity is the angular momentum. So angular momentum is denoted by N, and its expression can be written as, we have to recall this point, vector L is equal to R cross P. It is the vector product of perpendicular distance and linear momentum of that particle. This L is perpendicular to R, it is perpendicular to P also. So its direction can be determined by right hand thumb rule. It is, if it is shown like this, it is a particle of mass m, its linear momentum is P, R is the perpendicular distance of this particle or radius vector, then L is along the axis. So here by magnitude, for this figure or for this situation, L can be equal to product of R and P, and P we know it is equal to M into V. So here MVR, this can gives us the magnitude of angular momentum. These simple points we have to use in the derivation of angular momentum. So here we consider a rotating body of irregular shape. Axis of rotation is shown, which is perpendicular to plane of figure. We have to consider the body in this way, and axis of rotation is perpendicular to plane of a body or plane of the section of body. Here body is consisting of n particles. Here we can write there are n particles we have to consider, and having masses m1, m2, m3 up to mn. Their distances from the axis of rotation can be shown here. For the first particle it is r1, for the second particle m2 the perpendicular distance is r2, for the third particle of mass m3 the distance is r3, for the nth particle distance is mn. Now their linear velocities can be shown here, v1, but before that, here as the body is rotating in this way, it is with constant angular velocity omega. Its linear speeds for all particles can be shown like this, v1, v2, v3 up to vn. As here we have to use the quantity linear momentum. Linear momentum, here P is equal to m into v. Its vector equation is like this. Vector P is equal to m into v. Direction of linear momentum is same as direction of velocity. So here we can show another vector P1, here P2, for this third particle it is P3, and for the last particle it is Pn, like this. So once we know such quantities related to each mass, we can write the expression for P. First we write the expression for P. So here R1, R2, R3 we have to note these are the shortest distances. P1 can be written as, for the first particle it is m1 v1. It can be equal to m1 into r1 omega. Now for the first particle we write L1. Here this is for first particle. L1 can be equal to, here it is R into P. R into P is R1 P1, is R1 into P1 is M1 R1 omega. So we get M1 R1 square omega. This is the expression for angular momentum of the first particle, and from our basic points we can show its direction along the axis of rotation. This is for L1. And as all particles are in the same plane, we have considered here body is in a plane and axis of rotation is perpendicular to the plane of a body. Then for all particles we have to show such angular momenta. So for the second particle, L2 is equal to m2 r2 square omega. For the third particle it is m3 r3 square omega. For the last particle it is ln, can be mn rn square omega. Now all these angular momenta, we can take their algebraic sum, then we get the total angular momentum of the body. Here L can be equal to L1 plus L2 plus L3 up to Ln. Substitution gives us m1 r1 square omega plus m2 r2 square omega, m3 r3 square omega, and this sum extends up to mn rn square omega. Taking omega outside the bracket, m1 r1 square plus m2 r2 square plus m3 r3 square up to mn rn square inside the bracket and multiplied by omega. This is the expression for angular momentum. It can be written as here L can be written as, this bracketed quantity can be written, you know, it is moment of inertia for all particles inside the bracket multiplied by omega, and it is equal to I into omega, where summation of mi ri square is the moment of inertia. I is moment of inertia about the given axis, about the axis of rotation, given axis of rotation. So this is the expression for angular momentum in terms of angular velocity. In the basic point we have the relation for angular momentum in terms of linear velocity. It is now in terms of angular velocity. So here we have derived one expression. Now, like the law of conservation of linear momentum, here also there is law of conservation of angular momentum. So that we study here, law of conservation of angular momentum. It is also very simple to prove the law as well as discuss the law. Let us revise the law of conservation of linear momentum, because this angular momentum is analogous quantity of linear momentum. Here, according to law of conservation of linear momentum, if force acting on the body is 0, then P remains constant. Similar or analogous statement for the angular momentum. If torque acting on the body is equal to 0, then L remains constant. This is the statement. We can make the statement like this. If the external unbalanced torque acting on the rotating body is absent or it is 0, then angular momentum remains constant or angular momentum is conserved. In simple words, it is written in book that angular momentum of a body is conserved if external unbalanced torque is 0 or absent, or in the absence of external unbalanced torque, angular momentum remains constant. This we have to prove. So first we write the statement in short, and if tau is equal to 0, L is constant. How can we prove it? It can be proved by considering again the basic relation. This we have revised, which is vector L is equal to R cross P. So by considering this relation, we prove here the statement. How can we prove it? So when the body rotates, as the time passes there, then it remains constant if tau is equal to 0. So taking derivative on both sides or differentiation on both sides with respect to t, dl by dt is equal to vector r cross dp by dt, or derivative of t with respect to time, plus dr by dt cross t. So we have taken first term constant, and in the second term is constant. Here dl by dt is equal to r cross dp by dt is the rate of change of momentum, and according to Newton's second law, it is a force, r cross f, plus dr by dt, it is the rate of change of r, it is velocity vector. It is the rate of change of position vector, it can be a velocity vector, multiplied by m into v. P is the product of m into vector v. So here this second term v cross mv, we write it as m into v cross v. Self cross product is there, it is equal to 0. Now r cross f, this is also the basic relation. It is called as moment of force, or it is termed as torque. It is denoted by tau. It is equal to tau plus 0. dl by dt is equal to a vector tau. I can write the relation here. dl by dt, it is equal to vector tau. This rate of change of angular momentum is equal to moment of force or torque. So if here we take torque as 0 and taking this as the scalar equation, tau is equal to dl by dt. If tau is equal to 0, then L is equal to constant. Means angular momentum is constant. But just we have derived it is equal to I omega. Means I omega also remains constant. If there are 2 or 3 situations in which the moment of inertia is I1 and angular velocity is omega 1, in another situation moment of inertia is I2 and angular velocity is omega 2, then I omega 2 remain constant. We can write I1 omega 1 is equal to I2 omega 2. Similarly, here as this omega is related to n, we write I1 twice pi n1, I2 twice pi n2. So I1 n1 can be equal to I2 n2. So these are some relations we can write for I omega to be constant. So if tau remains constant, L remains constant, I omega remains constant, or I1 n1 is equal to I2 n2, I1 omega 1 is equal to I2 omega 2. Any relation we can write for the to show the constant angular momentum. So this is the proof of statement of law of conservation of angular momentum. Now we have to consider the examples of this conservation law. The first example we take of ballet dancer. Ballet dancer. For the ballet dancers, they have to rotate about their bodies. So the rotation may be faster or slower. So if they want faster rotations, they have to increase their speeds. Means angular speeds must be increased. What they have to do, they must have to decrease their moment of inertia. So for faster rotation, omega must be large but I should be small. So for that, ballet dancer do one thing, that they fold their bodies. Folding the bodies or taking arms and legs close to body, they can decrease the moment of inertia so that their rotations are faster. Means omega is large or n is large. So when they dance by having larger number of rotations about their body, their dance can look attractive. For that, they have to decrease their moment of inertia by folding the body. Folding the body means keeping the arms and or taking arms and legs close to the body. Now the second point they can do here, if they want slower rotations, means they have to decrease the angular velocity, they have to decrease their frequency, then they can increase the moment of inertia by stretching the body. Stretching the body means here they have to take their arms and legs away from the body. So while dancing, they take their arms and legs away from the body, means they stretch the body, they can increase the moment of inertia so that their frequency decreases, their angular velocity decreases, and the motion or rotations are slower in that case. So such examples you can read in book. So this is the first example. Also in the book, diving example is given for the divers. So this is one sport activity. While diving, they have to stretch the body so that their frequency decreases or angular velocity decreases. They can take so many somersaults there. Somersaults means undertaking so many rounds about the body. For making the somersaults, n should be large or omega should be large. For that, they decrease their moment of inertia, means divers decrease their moment of inertia by again folding the body. Same is the case, folding the body, they can decrease their moment of inertia so that they can increase the frequency of rotation, means they can take number of somersaults in air so that we can observe the attractive activities of divers when they are in air. But when they go towards the water surface, they outstretch their bodies, means they increase the moment of inertia so that they can take the entry in the water. That is called as diving. So this principle of angular momentum, principle of conservation of angular momentum usually used by divers as well as ballet dancers. So this is about the application or examples of law of conservation of angular momentum. Now the next quantity in this chapter is the moment of force or torque. It is the torque. This torque is denoted by tau. Just we have taken its introduction. Tau is the quantity, is a vector quantity. Its basic relation is vector r cross f. So f is the force acting on a particle which is situated at distance r from the axis of rotation. Then tau is equal to r cross f. Tau is perpendicular to r as well as force. Or also we can say that tau is directed along the axis of rotation and perpendicular to both r and f. So from this basic equation, tau is equal to r f. Here we have to derive the expression for torque for the rotating body. Again we consider the rotating body of any shape. Here axis of rotation is shown like this. But in this case, the body is rotating with constant angular acceleration. Means here angular velocity is changing. It is continuously increasing or continuously decreasing. But here we take it as continuously increasing. So here alpha is constant angular acceleration. When body rotates, it is accelerated. Angular acceleration is constantly increasing. For that, we again consider the body consisting of n particles. These particles are having masses m1, m2 up to mn. Their respective distances are r2, r1, r2 up to rn, like this. So for the first mass, the distance is r1. For the second mass, distance is r2. For the third one, it is r3. For the nth particle, here mn is the mass and distance is rn. But in this case, we have to find out the relation for force acting on each particle when it rotates. So for the first particle, force can be given. So I write here force on first particle, on the first particle. F1 denoted by small letter F1 is equal to m1 a1. This according to Newton's second law. So if we write the vector equation, this vector F is equal to m1 into a1. So a1 is the tangential acceleration. In this way we can show, and in that the same direction F1 can be shown. So for the force we write this equation, but we have to write for the torque or moment of force. Torque is equal to R into F. So here R1 into F1 for the first particle, R1 into F1. It can be R1, F1 is M1 into A1. But F1 also can be modified. Here we write again, we consider again the first step. F1 is equal to M1 A1, but this A1 is related to alpha in this way, R1 alpha. Tangential acceleration is R into alpha. Here we have to take this basic relation. Tangential acceleration is related by alpha with alpha by this relation, A is equal to R alpha. So here A1 we have substituted R1 alpha. This can be substituted in this equation, R1 M1. So let us continue this equation. A1 is R1 alpha. We get here M1 R1 square alpha. This is the torque acting on the first particle. So you can write the torque acting on the second particle, third particle like this. Here I write torque acting on the first particle as the final state here. This τ1 is equal to m1 r1 square into alpha. For the second particle, it is m2 r2 square into alpha, so that you can continue writing up to tau n. This mn rn square into alpha. All these torques for each and every particle, they are directed along the axis of rotation. The total torque is along the axis of rotation if the plane of rotation remains same. So this is one point we have to note. If plane of rotation is same, then torque is having same direction. Torque is along axis, along the given axis. So here I can show here the body axis of rotation in this way. Plane of rotation is maintained. It is suppose horizontal plane, but sometimes it may happen that this body can rotate in another way or another plane it can take. But in this expression we have to maintain the plane and we have taken it as a horizontal plane. In that condition, tau is vertically upward here or along the axis here. Tau can be written as tau1 plus tau2 up to tau n, and it can be m1 r1 square alpha plus m2 r2 square alpha. The sum extends up to nth particle, and inside the bracket we take again the same expression we get, which is the bracketed quantity always we have taken, and it is moment of inertia. This quantity is moment of inertia. It can be expressed in summation form, where summation extends from 1 to n. So we get tau is equal to I alpha. Tau is equal to I into alpha. This is our final expression. This bracket is replaced by summation. The summation is nothing but the moment of inertia along the given axis of rotation. So this expression also analogous to force equation. It is m into a. So each new quantity we derive, we discuss, and it resembles or it is analogous to some linear quantities. So in this case, tau means torque acting on the body is I alpha. Here force acting on the body is, suppose F is equal to ma. So these two are analogous equations. Like the kinetic energy, angular momentum, torque, these are analogous to each other. This is about the expression for torque when the body rotates with constant angular acceleration. This is the derivation. These derivations which we have studied today, they are asked for short answer question type 2, means for 3 marks, and their numericals also can be asked for 3 marks. Sometimes short answer questions of type 1 also can be asked on these simple derivations. So today we'll stop here. Thank you.